Hello, my name is Hari Iyer and I would like to present our work titled Real-Time Task Detection and Digital Twin Modeling using Human Posture Estimation in 360-degree videos. This is a position paper, which means there is a larger study underway, and this current paper presents our initial findings and our general methodology. I'd like to give a shout out to my co-authors, Dr. Ricardo Iris, and my doctoral advisor, Dr. Heejun Jong. We're all at Arizona State University. So what is a digital twin? It is a virtual model that replicates a physical object or system in real time. It can be used for monitoring and analysis by what I like to call information fusion. Information could be retrieved from sensor data, AI techniques, like deep learning, computer vision, and other visualization methodologies. The traditional applications of digital twins are in manufacturing, aerospace, healthcare, or any of those domains that involve either humans, processes, or the interaction between the two. However, more contemporary applications include human-centric fields like occupational safety and ergonomics, which revolve around worker safety. What is the use of modeling human activity, be it physical tasks, in some cases repetitive tasks like construction work or culinary work? The foremost reason is safety and ergonomics. Analyzing human motion can help reduce the possibility of injuries, improve workplace safety, and also make the workforce more productive. The challenges of traditional approaches include wearable sensor or marker-based motion tracking systems, which are not totally non-intrusive, meaning it might include putting on-body sensors, which could potentially hinder the naturalistic workflow of someone performing a task. 360-degree videos and AI-powered posture estimation can somewhat alleviate this issue, meaning it can provide a non-intrusive, imagery-based real-time analysis of human movement, and it could help with better risk assessment and training simulations. The motivation and objective for this work is mainly based on the past data. So ladder-related tasks are high-risk activities in occupational settings. So these could include ascending a ladder, performing some work while on top of the ladder, and also descending the ladder. The U.S. Bureau of Labor Statistics, in 2024 reported that 2.7 injuries occur per 100 workers in private industries, and similar rates have been seen in the construction engineering, in the construction management and construction engineering field specifically. Real-time monitoring and task detection can help identify postures or actions that might be involved in tasks that are not totally safe. Improve worker training and hazard prevention. It could improve ergonomic assessments to reduce musculoskeletal strain or musculoskeletal disorders in general, often referred to as MSDs. Using 360-degree video and AI-based posture estimation can create a scalable model for this. The objective of the study is to develop a human-centered digital twin using task detection, human posture estimation, and Gaussian splatting. The related work in digital twins, so traditionally used in manufacturing and other industries, as I went over in a previous slide, the emerging applications in human-centric domains such as construction safety and worker monitoring. Some of the previous studies have relied on fixed camera systems. So these are camera systems that don't necessarily move. They have a fixed field of view that limits the amount of the environment that is visible for analysis. So the current study actually uses a 360-degree video camera that captures everything in the surrounding to make sure that if there's multiple workers, for example, in the environment working, then all of them can be captured in video. Traditional motion tracking systems rely on marker-based systems. One of the prominent examples is the Aruko system, where the on-body markers are put, or the markers are put on whatever surface needs to be monitored, which involves some pre-processing, and also it's not totally non-intrusive. Thus, Markerless poster estimation algorithms, which are performed using computer vision, have been very popular recently. OpenPost and MediaPipe are two most prominent examples of poster estimation models. Task detection can be used to analyze body posture and segment the activities based on what the worker is trying to do. So for ladder-related tasks, in this study, we considered three different tasks: ascending a ladder, working while on the ladder, and descending a ladder. So kinematics-based joint detection and the joint angle detection specifically can be used to classify these tasks. And a probabilistic technique can be used to create a model to assess the task being performed and to classify them for further analysis. The proposed framework is shown in this figure. So we have a 360-degree camera that captures the frames of the that captures videos and subsequently converted into frames of the workers performing the tasks. The human and the ladder is extracted from the frame using some pre-processing. We use MediaPipe to extract the posture of the worker. Then it is given to a PEUSGC model, which is a posture estimation based unsupervised spatial Gaussian clustering model that was developed at our lab, and it's published. Its reference is mentioned in the last slide. So what this model does is it takes different postural data. So it can be either near duplicate tasks or tasks that involve repetitive motion, and it can actually use that postural data to classify the tasks with higher accuracy compared to traditional convolutional neural networks that follow a pixel-based approach to classify images and try to identify the tasks from that. So from the videos, we plan to have a timestamp of the different tasks being performed using this model, and use the extracted human and the posture to create a high-quality digital twin model. So we had recruited 24 individuals, 12 male and 12 female. We had a gender balanced participant pool. They performed the three tasks. As I had mentioned before, we used a 360-degree camera, Insta360 X3 8K for motion capture. We also captured electromyography and inertial measurement unit sensor data. However, though, that is planned for a future study, and that sensor data is not directly applicable to the current study. The tasks were performed in a controlled environment to make sure the participants received standardized instructions for consistency. So the kinematic feature modeling and task classification was performed using firstly MediaPipe that extracted the 33 landmark points as was shown in the previous frame. Each frame provides the XYZ coordinates of the body joints. The key metrics of these landmark points included displacement, velocity, and acceleration in between frames, how the poster is moving between frames, and that's how the kinematics of the tasks were modeled. So Gaussian splatting is something that we are currently exploring. We tried to integrate that into our current system. However, the existing model was developed using a library called Midas in Python, but we are currently figuring out what is the best way to create the highest quality digital twin to have that twin perform certain tasks that might be otherwise risky to attempt by a human. So here we can see on the leftmost GIF, the posture is shown of the worker climbing up the ladder. The red points are the different landmark points that have been detected from the frame. The green lines actually join these landmark points to show the skeletal structure. So now they have climbed up the ladder, they're performing a task, and shortly you'll see them descending. The animation to the right of it actually shows the monocular depth estimation of the frame. As you can see, the yellow pixels in the GIF are the points that are closest to the camera lens, and it gets darker as it goes further in space. And on the right is a digital twin that was stitched up using the data that was gathered. We look forward to scalably doing this for data from all the 24 participants that was captured. So the conclusion is that we developed a human-centered digital twin. It demonstrated real-time, non-intrusive task detection, And we look forward to expanding this to GPUs for scalable performance and also AR and VR visualization. These are the references, and we are thankful for you to listening for your attention. And if you have any questions, please feel free to email me at hnir@asu.edu. Thank you so much.